What's going on, guys? Welcome back to another YouTube video, and in this video we are going to be talking about ways to classify different computer algorithms. So without any further ado, let's get started. Alright, so the most common way to classify a computer algorithm is by looking at its complexity, or basically the time it takes to complete a task given the size of a problem. In this video, we're going to be talking about three different types of classifications. One of them is going to be constant time. The other one is going to be exponential, which will be like this. The final one will be linear. Alright, so I'm just going to give you an example of each type of time taken to complete and the graph for that. So let's say I have a program that tells me whether a number is even or odd just by looking at the last digit of the number. And if that last number is 0, 2, 4, 6, or 8, that number is going to be even. And if the last number is any other number, then it's going to be odd. Okay, so the time taken to complete this algorithm is always going to be the same no matter the size of your input, because it doesn't matter how long the number that you give it is. It's just going to go all the way to the end and read that number. Everything else basically does not matter. So essentially, the computer only looks at one digit of your input, and that's going to be the same for every scenario. So that's why it has constant time. Now let's say I have a program that does addition. So with addition, it's going to have the two numbers and it's going to add them. So what is going to be the time taken to complete for an addition program? Well, that would have a linear graph, because every number that you add at the maximum, it's going to give your answer one more digit. So what happens is, if you increase the size of like an adding algorithm, then the time taken to complete increases, because each extra digit or size of your algorithm. And an important distinction that we have to make is that different computers or different devices will do these tasks at a different rate. But even though these devices have their differences in time taken to complete, for example, a computer can add a lot faster than a human can, the growth rate for these problems will be the same. And finally, let's say that we have, okay, and for this final example, let's say I have a pin of size n, and my goal is to just randomly guess all the numbers in from that range. So let's say n is 4. My job is to guess a number from 0000 to 9999, and just keep on doing that until I guess the right number. What happens if n now becomes 5 instead of 4? So now I go from having a max of 9,999 to 99,999. Alright, so let's say I have a one-digit number. That number can go from 0 to 9. But if I have a two-digit number, that number can go from 00 to 99. And guessing in a scenario like this, the range is a lot larger. So the time that's taken to guess the number will be a lot larger. And in addition, where, if you added a number, so let's say I have 15 plus 2, that would be 17. But if I have 15 plus 22, that would be 37. And although I still did these problems at the same rate, if you really hone it down to like the millisecond of like computation, if you test the time that it takes for a program to do this, you will notice an increase in the time that's required. But what happens is, let's say I make this 15 plus 222, this number will be 237. But what happens is adding another digit does not make the problem exponentially harder as it does in this scenario. It just makes it a little bit harder, but still manageable. So that's why the graph we're guessing a number wouldn't be an exponential graph, which means that it grows faster than a linear or a constant time graph. So yeah, that's it for this video, guys. Thank you for watching. I hope you enjoyed. Don't forget to like and subscribe, and I'll catch you on the next time. Peace.